Pierre Cristofari. So just a quick summary of Pierre. So Pierre is an expert on high energy astrophysics, so gamma rays and cosmic rays. He did his PhD at APC in Paris, and then a few postdocs at in Italy, also at Columbia in New York. And now he's an associate astronomer at Observatories of Paris, so the Lux group.
Yep.
So please, Pierre, you have 45, 50 minutes, and then a few questions.
Perfect. Thank you very much. Hello, everybody, and thank you to the organizers for having me. Thanks for being here. The title of the talk is The Origin of Cosmic Rays and Gamma Ray Astronomy, and as requested, I will assume that nobody knows anything about cosmic rays or gamma ray astronomy, so I'll try to make a general introduction. If inadvertently I'm using some sort of jargon or acronyms or whatever, please feel free to interrupt and just shout or raise your hand, whatever, and I'll try to make myself clear. Cosmic rays are charged particles, 90% protons, but also electrons, heavier nuclei, coming to us from all directions of the sky with a very good isotropy. They come from everywhere at relativistic energies. The most famous plot of cosmic ray physics is this one. It's called the local cosmic ray spectrum, often called the local interstellar spectrum. And it's basically a number of particles coming as a function of the energy. So in fact, a number of particles per unit energy, per second, per square meter, per steradian, or flux of particles, as a function of the energy. And in the words of the late Professor Tom Geiser, who wrote an amazing book in the 90s on cosmic ray physics, the most fundamental question of cosmic ray physics is, where do they come from? How are they accelerated to such high energy? Because here, the energy is, we're mentioning here on GeV. I don't know if it makes sense to you, but just to give you a sense, those energies here are tremendous energy, several orders of magnitude what you can produce on Earth. Here, we have written, for instance, for a few particles coming here, the equivalent in LHC energy. So LHC will be here, and we're reaching a few orders more than what we can produce on Earth, right? And so on these plots, you see various colors and dots and points, and those are decades of experiment who've helped measure this local cosmic ray spectrum. And the remarkable feature is that you have a power law going down in energy. At low energy, you have a slope e to the minus 2.7 up to a region called the knee, where the spectrum breaks is roughly e to the minus 3, and then again some variation and so on. Some of those features are very well known. This is called the knee. This is called the ankle, because somehow people see that this looks like a leg, right? The knee and ankle. And how do we measure those cosmic rays? So I mentioned you have a fair bit of experiments here, and many more, in fact. But just a few very famous. This one is called AMS-02, installed on the International Space Station, measuring cosmic rays at low energy, let's say. You have, for instance, another one, a space telescope, a space instrument called DAMPE, the dark matter experiment and particle experiment, dark matter and particle, Chinese observatory, and another one at the highest energy, the Pierre Auger Observatory, now called Auger Prime, I believe. This is installed in Argentina, and you have water tanks that help detect particles at the highest energy. So you see a variety of experiments to detect the cosmic rays all over the energy spectrum. Usually, what we have understood of cosmic rays is that at low energy, the origin has to be galactic for various reasons, but mostly for confinement. You know, the particles are confined in the galaxy, so the origin has to be galactic. At the highest energy, it has to be extragalactic, because there's no way you can produce these particles inside the galaxy. And in between, well, it's complicated. That's basically the story. In this talk, I will focus on the lowest energy of the spectrum. Let's say this part right here, so the galactic and its complicated part. But discussing, in fact, that everything is a bit complicated, so it's not, yeah. Why is it so difficult to understand the origin of cosmic rays? What are the sources? How are they accelerated? Well, in fact, so as I mentioned, the cosmic rays are charged particles, protons, electrons, and so on. So they are deflected by magnetic field. Therefore, when they come to us, when they arrive, the arrival direction does not point back to the source, right? Because they've been deflected by galactic, extragalactic magnetic field. However, this is not the case for photons. So we can use, if they produce photons close to the source, we can use that to understand where they come from. Slightly, OK. the minimum requirement on the proton sources, so this was the bulk of the cosmic ray spectrum. I messed it up here. So the protons are all the way up there on the local cosmic ray spectrum. And the minimal requirement that you want on the sources, you want to make sure that your sources, whatever they are, they produce the correct amount of particles to sustain this level of cosmic rays. You want to make sure that the slope is correct, is compatible with what we measured. And we want to be able to reach this part here around the knee for the galactic sources, right? So, photons. What kind of photons? We have cosmic rays. What kind of photons? Well, this is where the gamma ray part comes in. Cosmic rays, accelerated particles at the highest energy, are expected to produce gamma rays. And these gamma rays can be detected. One example is this instrument here. This is called the High Energy Stereoscopy System, HESS. Some of your colleagues at the CPPM are involved in Marseille. And this is several countries are involved in Germany, France, and so on. This is installed in Namibia, and it's been working for maybe 15, 20 years now. So it's very well working. Another example of instruments to detect gamma rays is the CTAO, the Cherenkov Telescope Array Instrument. This is an artist view here. So this is an array of telescopes that will be installed in Chile and in the Canary Islands. So on two sites currently being built. I can show you a picture of the first telescope that was installed. This was in 2018. So this is a 23-meter diameter telescope here. So this is designed to detect the gamma rays typically in the TV range. So this was the first one installed. The first light was at the end of 2018. And now we are currently building 3 more around them. So there will be 4 large-size telescopes, and that will make probably, we can say it safely, the best instrument in the TV range. Best sensitivity, best angular resolution. So this is a view from a drone taken from the CTAO website, and you see that the dish are being installed here for this 23 meters diameter telescope. And so expected this will be probably functioning, we always say next year, but next year for real, we'll have the data. So CTAO, another example of gamma ray instrument. But that's not only this. I will also talk about this instrument here. This is LASSO, another Chinese observatory, but this time installed in the mountains in Sichuan, the large high-altitude air shower observatory, currently working. And here, so it's a little bit less fashionable because you have tanks installed on the ground and in this facility here. So those are water tanks with detectors. So, but this is very impressive and also providing very important scientific results. The principle of working of all these experiments is basically the same. You have an incoming gamma rays coming from the sky, right? Potentially from a source of cosmic rays. And this will collide with nuclei of the atmosphere, providing a shower of particles. These particles will be relativistic, going faster than the speed of light in the atmosphere, right? So this will produce a Cherenkov light, a flash of blue light that we can detect. So you can detect this light in the atmosphere with the Cherenkov instrument, such as HESS or CTAO, just as I showed, or using particle detector, for instance, water tanks with a photomultiplier, and you detect the blue light as the particles pass by. If you have an array of those detectors, you can reconstruct the cascade, and therefore reconstruct statistically the incoming particles, the incoming gamma rays. And that's how you do gamma ray astronomy. And the technique is working very well now, and you can typically have resolution of the order of the arc minute. So for real astronomers, sometimes a bit like, are you sure you said arc minute? Yes, yes. But in the gamma ray domain, this is quite good. So this is to give you a sense, and I will show you a few images in the following. So that's the principle of those experiments. I mentioned about the sources of cosmic rays, what we expect, what we want for the sources to explain those cosmic rays. And I said, so we expect, because of the local cosmic ray spectrum, that the sources can provide the amount of cosmic rays we measure. I haven't written the number, but just to give you a sense, the energy density in cosmic rays we measure is of the order of 1 electron volt per cubic centimeters. And this is roughly of the order of the energy density that you have in the magnetic field or in the thermal gas in the galaxy. So this is an important component of the galactic ecosystem. So it's a fair amount of cosmic rays you want to produce. So you want to sustain this cosmic ray power with your sources. So you need this. You want to explain this slope that we've seen in the cosmic ray spectrum. And finally, as I told you, you have a region where the slope is breaking from e to the 2.7 to e to the minus 3. And this is called the knee. And because of the confinement of the cosmic rays in the galaxy, you expect that the sources are able to reach the knee. And this is why people have been focusing a lot. And the knee is located at 10 to the 15 electron volts, so PV energy in the jargon. So we expect the sources to be pevatrons. And this is why, at the core of the scientific proposal of all these experiments, Hess, CTAO, LASSO, you'll see the word pevatrons, looking for pevatrons, pevatrons. Because for a long time, it has been said, if you find the pevatrons, you unveil the origin of cosmic rays. A result from particle physics is telling you that if you have protons of PV energy, 10 to the 15 electron volts, so pevatron, the expected gamma rays is roughly a factor of 10 below, meaning that if you detect gamma rays of 100 TeV, you'll be probing the presence of PV particles, right? Factor of 10, this easily understood. This is why all these instruments, typically capable, more or less, not this one, but this is why we're building the new one, capable of detecting 100 TeV gamma rays, detecting the pevatrons. What about those pevatrons? Well, in fact, we already know a few pevatrons in the galaxy. The first experiment, Hess, as I showed, to claim the detection of a pevatron in the Galactic Center was in 2016. They were not able to directly probe the 100 TeV gamma rays, but you could see, or you could go up to a few tenths of TeV with no sign of exponential suppression. So you see a spectrum going up and say, well, it's unlikely that it's cutting like this, so it's probably going all the way to the 100 TeV. So that was the first claim of a pevatron in the Galactic Center 10 years ago. And then came LASSO, so the Chinese in-the-mountain instrument, detecting not 1, but 12 galactic pevatrons in 2021, to give you a sense, with a clear detection at high energy. And more recently, a couple of years ago, providing a catalog of 90 sources with 43 clear pevatrons all across the galaxy. So this is the current status. Now we've detected more than 40 pevatrons. And I wouldn't be surprised that they provide a new catalog very soon with even more sources. In all these cases, it's not, OK, so we clearly have pevatrons. But one thing I haven't told you, it's not clear if those pevatrons are clearly coming from accelerated PV protons. Because in fact, it could also be accelerated PV electrons. This, a few years ago, was not well understood. So let me explain. I mentioned that the accelerated particles can produce gamma rays. But in fact, in the very high energy domain, you have two ways of producing gamma rays. You can produce them with protons. You have accelerated protons interacting with the interstellar medium, nuclei, producing pi0 and the pi0 decay and produce gamma rays. So that's what I talked about recently. But you also can have gamma rays from accelerated electrons interacting with low energy photons, for instance, with photons of the CMB, or optical photons from, that will be upscattered, producing gamma rays. So you have those two competing mechanisms that can produce TeV gamma rays. The spectrum from accelerated protons, so this we call hadronic interaction, but at some point, I think I was in a CNRS interview, I was mentioned that I should not use the word hadronic leptonic because it was barbarian. So, but we refer to this as hadronic interaction and this as leptonic interaction because it involves hadron and lepton. So in the hadronic interaction, the spectrum you expect is mimicking the parent proton spectrum. So if you have a power law in protons, you get a power law in gamma rays. And as I mentioned, you cut off at 1/10 of the energy of the protons. And if you have a leptonic interaction, you expect to have a spectrum of gamma rays which is a bit more bumpy, and also that is suppressed at the highest energy a little bit earlier on. And this is because of an effect in the cross-section that's called the Klein-Nishina effect, but let's not go into details. So you expect this spectrum to be bumpy and cut off at lower energy. And for a long time, because we had instruments such as Hess operating in this range, it was very hard to differentiate between the protons and between electrons. And for a long time, people were saying, well, if we build CTAO and we have instruments optimized here, then you'll be able to differentiate and say this comes from hadrons, this comes from protons, or electrons, protons. And this is why a lot of motivation on detecting the 100 TeV gamma rays to probe the acceleration of PV particles. But when the LASSO result came in, people realized that, in fact, well, you cannot really probe protons, differentiate protons and electrons in this range. In fact, it's very hard, and most of the sources here that naively would have been proton sources are, in fact, now interpreted as electron pevatrons. So it really asks the question, how do you differentiate between leptonic, hadronic pevatrons, so electrons, protons? What sources can accelerate a sufficient amount of PV protons? Because in the context of cosmic rays that are mostly protons, we are still interested in finding the source of PV protons and bulk of protons. So physically, I mean, astrophysically, what can those sources be? Well, in fact, the proposed theoretical sources for the cosmic ray, the bulk of cosmic ray protons, have been very various. You've had massive stars, microquasars, superbubbles, supernova remnants, mildly relativistic jets from fast optical blue transients, supernovae, and I could add a few more. So a large variety of proposed candidates for the sources of bulk of cosmic rays. For a long time, the most famous candidates were supernova remnants, so the shock expanding in the interstellar medium after the explosion of a massive star. And this is for a variety of reasons. The first reason was theoretical from a calculation. You can explain this very well. But the best evidence was probably the detection with gamma ray instruments of spherical shocks accelerating particles at the very high energy. This is an image of ALICE J1713 -3846, which is probably the best studied supernova remnants in the TV domain. And you clearly see a spherical shock expanding in the ISM. This guy is probably 1,600 years old, around this. The image is a little bit blurry here, so you may ask, it's not because I took it from a PDF. It's actually because of the resolution of the instrument, right? Because we're limited in resolution. And this is the best example of what is called a non-relativistic, collisionless, strong shock. Non-relativistic because it goes, the shock wave goes more slowly than the speed of light. Collisionless because the interaction in this diluted plasma are not mediated by collision of particle-particles, but particles-wave interaction. And strong shock because the velocity is still highly supersonic. And therefore, this is the perfect setup to have this mechanism called diffusive shock acceleration, where you accelerate particles with a power law that is which is compatible with observation and so on. So a mechanism that is very efficient to accelerate particles and that we think we understand very well. So this explains why supernova remnants have been so fashionable in the world of particle acceleration and for the origin of cosmic rays. So we have observations in the very high energy domain, but not only. If you go on the other end of the electromagnetic spectrum, so in the radio domain, those are a few images I took from Meerkat and the gigahertz domain. So it's just for the pleasure of showing some very nice supernova remnants and show you how. So now the image is not blurry anymore, you realize, because the resolution is exceptional in this energy domain with Meerkat. So this is one SNR. I don't even know his name. I wrote it somewhere. But you see, it's spherical. It's very nice. And you also have a variety of objects. This one is the bird supernova remnant here. It looks like a bird a little bit. You see, it's not a bubble directly anymore. Then you have a flower. This is another one. You see, also it looks like two bubbles on top of each other. And the final one, this looks like I don't know. Sometimes I see a mouse. I mean, it depends. You can talk to your shrink about this. It's another supernova remnant, a great diversity of objects in the sky. And also, if you look at the center of the galaxy, they provided this map, which is quite, maybe you have too much light, but you can see the center of the galaxy here with a few supernova remnants, clearly spherical. And it gives you a sense of the resolution of the instrument, which is quite amazing. You see one supernova remnant here, another one over there, and you have another one, Sagittarius, J359 right here, so showing those spherical shock expanding. In this part of the spectrum, those are not protons. These comes from accelerated electrons radiating through synchrotron and providing the radio image. But still demonstrating that you have particle acceleration. Thank you very much for the light. So going back to the case of supernova remnants, So we want the sources to be able to account for the number of cosmic rays we have, to account for the slope that we measure in cosmic rays, and to reach the knee to be pevatron, this I mentioned. With supernova remnants, if you take a fraction of the explosion energy and convert it into cosmic rays, you can explain the amount of cosmic rays you have, and that's fine. For the spectrum, let's say it's more or less fine, because with the diffusive shock acceleration mechanism I mentioned, it's sort of working. And what about reaching the knee and the pevatron? Well, there's still a point that is highly debated. If you want to estimate the maximum energy that you can reach at an accelerator, the absolute maximum you can do is set by the Hilles criterion. The Hilles criterion is basically relating the diffusion length of particles to the size, connecting it to the size of the accelerator, and you can estimate the maximum energy you can reach. And in the case of supernova remnants, this gives you this formula. The maximum energy is a fraction of the shock, the radius of the shock, velocity of the shock, magnetic field. And if you plug in the appropriate numbers, and you want to go to the PV range, you realize that, of course, the radius and the velocity, it is what it is. So the one thing that has to be substantially higher than the ISM value is the magnetic field. But if you have the correct value of the magnetic field, then you can reach the PV range potentially. From observation, this is what people have measured. The magnetic field at supernova remnant shock. So this is the magnetic field energy density as a function of velocity of the shock. So the young supernova remnants are here. The older one have slower shocks. And you see indeed that the value inferred from X-ray measurements, for instance, are substantially higher than the magnetic field of the ISM. So the magnetic field observationally looks that it's high enough to provide the PV acceleration. Theoretically, we also understand where it comes from. The consensus is that the accelerated particles at the shock, so the cosmic rays, will go stream in the plasma and excite instabilities in the plasma. And those instabilities, there are many ways to excite the instabilities, but we understand now that the fastest growing instabilities are driven by what is called the non-resonant streaming instability. That's a little bit of jargon if you've never heard it, but so it's an instability, the fastest growing instability that will amplify the magnetic field. And we can estimate the maximum momentum of particles. So momentum energy is all the same for me, right? The maximum energy of particles has a very simple function of the radius of the shock, the efficiency of acceleration, the density that you have, and the velocity of the shock. So we can estimate the maximum energy, theoretically, that you expect from this streaming of particles in the plasma, excitation of instability, that amplify the magnetic field. And of course, so this is a very simplistic formula, very simple. But this can be different for the variety of supernova remnants. As I showed, you have a great variety of supernova remnants. And so this can change substantially. In the world of supernovae, you basically, and it's a rough description, but basically you have two types. Type 1a supernovae, thermonuclear supernovae, and type 2, what I will call type 2, which are all the core collapse supernovae. Thermonuclear supernovae typically explode in a flat ISM, a flat interstellar medium of density n0, whatever, and that's what you have. You know. But for core collapse supernovae, it's a little bit different because you have a great variety in the mass loss rate of the wind, the velocity of the wind, the duration of the main sequence, the initial mass of the star, and so on. So typically what happens is that during the main sequence, the star will blow a wind that will inflate a low-density bubble. And in the late sequence of the star, typically the red supergiant, it will blow a very dense wind, slow, dense wind, that will create a higher density media. So when the shock explodes, it will go through a dense media, then a low density bubble, and finally reaching the interstellar medium. And this structured interstellar medium depends on many parameters. It depends on the mass of the ejecta, the total explosion energy of the star, the mass loss rate of the wind in the main sequence and the velocity, and also in the late sequence. So a lot of parameters to explore and to play on. But typically, this is a structure. Dense wind, low density bubble, unperturbed ISM, and the shock, when the supernova explodes, will go through this, and this. And so the maximum energy you can reach changes substantially, especially if the structure of the medium changes. If you have a higher mass loss rate in the red supergiant stage, for instance, you expect to have a higher density wind, and therefore a more favorable condition to reach the highest energy. So just to give you a sense, and of how far you can go in energy for the typical object you have. So this is the maximum energy of accelerated particles as a function of time. So this starts at 10 to the minus 3 kiloyears. So this is 1 year. And it goes to, let's say, this is 1 kiloyear. So it goes to almost 2 kiloyears, right? So for the typical type 1a, type 2, you typically at most get a few times 10 to the 5 GeV, so 0.1 PeV. So you are below the PeV range, that's the orange line. So for typical supernova remnants, you don't reach the PeV range using this formula and this understanding of magnetic field amplification and so on. So typical objects, you're below the PeV. If you start playing on the parameters, remaining in the realm of what's reasonable, for a few objects that I call type 2 star, which are nothing in terms of astronomy, it doesn't exist. I just call it 2 stars for me. So if you tune the parameters and you try to see how far you can go in energy, you can reach, for a few objects, providing that the mass of the ejecta is low enough, providing that the total explosion energy is high enough, providing that the mass loss rate is high enough, you can reach, for a few centuries, the PeV range as a maximum energy. So one result I wanted to show you, but I don't want to go into details because I don't want to bore you. But you can use what is the standard semi-analytical model to understand what are the protons created by a given object after propagation in the galaxy. So this is what I'm showing you. I'm warning you before showing you because so this is a typical one-dimensional cylindrical model where we assume that the sources are located in the disk of the galaxy, that the particles propagate in a halo above and below the galactic disk. And this is supported by many experiments, especially measurement of secondaries, electrons produced in the propagation. And so you can describe the evolution of the protons after propagation, solving this transport equation. So you have a variety of terms from the diffusion, advection, the injection from the sources, and you can solve this semi-analytically, basically. And if you play this game with the various supernova remnant types that I showed you, one result that we got is that if you inject protons from those types that can reach the PeV range, right, they have to be very unusual and very rare. So if you want to reach the PeV range with some type 2 star supernova remnant, then their rate has to be low. How low? Well, typically 1, 2, 3%, a few percent of the typical supernova rate in the galaxy. So I say it again, in order to be Pevatron and to reach the knee, the rate of those objects has to be low, 1% of the supernova rate. Otherwise, you would produce way too many protons at lower energy, and this will violate somehow the measurement. So if supernova remnants are sources of cosmic rays, galactic cosmic rays, and reach the knee, they have to be very infrequent. And actually, that's what LASSO has seen, because I mentioned this late catalog of LASSO in 2024 with the detection of 90 sources, 43 above 100 TeV, so 43 pevatrons. And one remarkable fact is that almost none of these sources was directly associated with a supernova remnant shock. So it's sort of in agreement with what I said for the supernova remnant case. Almost a day. In fact, in this list of 43 sources, there is one source that's called G106 plus 3, G106.3 plus 2.7, which is a very complex source from which very high energy gamma rays have been detected by LASSO and also other instruments like ORC. So it has been claimed to be a supernova remnant proton pevatron. But we did this recent work with some colleagues of the CPPM, actually, and we discussed that, in fact, it's very unlikely that this source of gamma ray is due to a simple supernova remnant shock. It's probably connected to the pulsar or something else, because to explain the gamma ray emission is not obvious at all. So even this source is not clear that it's a supernova remnant pevatron. So I've talked a lot about those supernova remnant pevatrons, how you reach the knee, and so on. But in fact, you also have other problems explaining the cosmic ray spectrum at lower energy. By the way, I realized at the beginning of the talk I showed you this plot here with the slope like this, and now I'm showing you something like this. It's just because I multiplied by e to the 2.7 to get something flat, so we can see better the deviation. But this is the same cosmic ray spectrum that I showed at the beginning. is a function of energy, number of particles, number of cosmic rays from various experiments. So in this plot, the PV range, the knee is here. But you see that with the current performance of the instrument, we are able to probe very subtle deviation of the cosmic ray spectrum. And this is not this perfect power law, e to the minus 2.7, that we thought it was at the beginning. Now we are able to probe a deviation at the percent level, and some surprises arise. For instance, this bump here provided by Dampe, so it's clearly showing something that is a little bit bumpy in the 10 to the 4, so in a 10 TeV domain. And this has to be explained. So not only do you want your sources to be able to reach the knee and so on, but you want to be able to account for those deviations with the sources of cosmic rays. One possibility, obviously, is that you would have several different classes of sources and different type of object that will provide the bulbs and deviation in this cosmic ray spectrum. This solution has been provided, or this possibility has been discussed in many places. For instance, this work here where they were discussing different classes of object of supernova, different types of supernova remnants associated to supernovae. And they were showing that if you add up the contribution for the various supernova remnants, then you were getting those bumps and deviation. It was actually predicted way before the Dampe bump. They were not trying to explain it, but they were getting it for free. And so this could be that indeed, so I'm putting the two plots on top of each other, that those contributions for various astrophysical sources are providing those bumps and deviation. But if we look into more detail, this work that was interested because compiling is now a little bit outdated because there was also provided those objects capable of going far beyond the knee, which is not the consensus anymore. We can also ask ourselves the question, would it be possible to provide everything with just one object? To provide the entire cosmic ray spectrum with one object? Because as you see, so this is the protons from unusual type 2 star object that I designed on purpose to try to account for everything. Here, you have to look at the red and dashed blue line. This is the sum of all protons. In fact, in this calculation, we differentiate between the particles that are trapped inside the supernova remnants and particles escaping for physical reasons. But let's not look into the details. The sum of all the protons is the one on the cumulative line here. And so the question is, can you find, maybe it's just that all the cosmic rays are provided by one class of objects, and if you find the right parameters, you can explain everything. So that's a possibility, but it always leaves with a major problem, is that it leaves you with almost no room for the other accelerators. And in the world of gamma rays, we see several supernova remnants, so we see that there are accelerated particles. If you provide the entire cosmic ray spectrum with one object, what are the others doing? So that's the problem. Even more, so in what supernova remnants are doing, in the modeling of supernova remnants, usually it is understood that when the shock starts to expand, so when the star explodes, the shock goes through a first phase that is called the free expansion. So basically, you have so much energy, and the mass of the ejecta is way greater than the mass of the swept up material here. So that's the first phase, free expansion phase. At some point, the mass of the ejecta starts to be of the order of the mass of the swept up gas, and you enter what's called the adiabatic phase, Stadov-Taylor phase. And this goes on and on until typically you reach what is called the radiative phase. The cooling time of the material behind the shock becomes of the order of the supernova remnant, and therefore the material downstream the shock starts to cool down, so things start to change a little bit. To give you a sense, if you are dealing with a typical type 1a supernovae, the typical orders of magnitude, the time of those different steps, the first step of the free expansion phase typically lasts for 0.3 kiloyear. The adiabatic phase typically 20 kiloyears. And the radiative phase, well, not very well understood. But if you look at the literature and the different descriptions, it's typically 100, 200 kiloyears, sometimes 20 kiloyears, which is the same number than this one, sometimes 300 kiloyears. So it's not well understood. But in any case, usually when people are talking about particle acceleration, they're focusing on this phase, when the shock is very energetic, strong, the material is going, and we see observation where we know the particle acceleration is taking place. And often, particle acceleration in the radiative phase is overlooked. because many arguments in favor of the fact, well, the material is cooling down behind the shock. The conditions are not very good for particle acceleration. Also, the shock is slowing down, so you don't have a lot of kinetic energy coming in. So, sometimes often overlooked. There is an interesting fact. There is one guy called David Green that is providing a very useful catalog of all supernova remnants detected in the galaxy. And this catalog has been doing this for maybe 20 years or something, even more, I don't know. And the last version that we have is in 2025, and he is now counting 310 supernova remnants. And basically, since the last version that was 6 years before, only 21 sources more. And those are typically just reclassifying H2 regions. And so this is to tell you that the number of known supernova remnants in the galaxy is very steady. It's almost like we've completed it. It's 310 supernova remnants. And if we do a naive estimate of the number of supernova remnants we expect, with a typical end of radiative phase of the order of 100 kiloyears, you will have that you have 3 per century times 100 kiloyears. So that's typically 3,000 objects you expect. So that's a factor of 10 of difference. So you may wonder, where are those supernova remnants? Are they just not supernova remnants because, in fact, the radiative phase is killing them very soon? What's happening between the 300 and 3,000? What's happening in the radiative phase? And this is actually something we've been looking in, trying to understand. For instance, at prototypical supernova remnants, what happens between the adiabatic phase, so that's the 20 kiloyear I mentioned here, and between the 300 kiloyears, so that's building up in time, the proton content that you expect at a typical type 1a supernova remnant. And so this is just to illustrate, also to advertise some recent work, but to say that there is many things we don't understand in supernova remnants, and especially the end of particle acceleration where it stops. This might be a detail, but also might not be a detail, because between 20 kiloyears and 100 kiloyears, that's a lot of time. That's a very profound remark. So understanding the end of particle acceleration, very important. So where are we at? So on the origin of cosmic rays and galactic protons especially. So what sources could be the pivotron? Well, it could be supernova remnants, but there have to be few of them and unusual, rare objects. Could be also many other sources, massive stars, superbubbles, and I'll say a word right after. How do you produce enough protons in a hard enough spectra above the PV range? This is another question I haven't touched, but not only you want to go there, but also you have all the spectrum that is extending here that you may want to start to try to account for. And so it leaves you with more questions than even before. What role plays all the other SNRs that cannot reach the PV range? How do you account for the features? So that's the current question that people are trying to understand. On the case of supernova remnants, in fact, so I mentioned the end of the radiative phase, but I just want to touch down on 3 problems so you get a sense of what people are working on. I mentioned that the spectrum provided by the mechanism, it's called diffuse shock acceleration, is more or less OK with observation. But this more or less is often not that OK. In fact, so the standard test particle theory is providing with the power law of accelerated particles, which is p to the minus 4. And we realized that to account for the TV gamma observation, usually you need something that's a bit steeper, so p to the minus 4.2, 4.3. And this is not completely understood. A second problem is that the overall injected spectrum, not only what is accelerated at the shock, but what is accelerated, what is put in the ISM after acceleration, after losses, after being trapped, and so on. Also, we have indication that this spectrum has to be steeper than p to the minus 4. Again, p to the minus 4.2, 4.3. So that's something that's not well understood at supernova remnants. And finally, well, the problem of the maximum energy, PV, and so on, I think I discussed it already. But that's a problem also trying to understand. Do we have at least this one object that is a clear pivotron? Was it in the past? This is not understood very well. All this is mainly for protons, but we don't only have protons. There are also some other problems. A very famous problem on explaining the sources of cosmic rays is the neon 22 over neon 20 ratio. We know from measurements in the local ISM today and from billions of years ago, and that there is a difference between this ratio on the local ISM and in the cosmic ray spectrum. And there is a factor of a factor of 4 or 5 difference in this ratio. And this is not easily accounted for with supernova remnants, with simple supernova remnants, as I discussed before. So explaining this overabundance of neon-22 in the cosmic ray spectrum is something that is very important. And this, for instance, has been pointed towards other possible accelerators, such as the stellar wind termination shocks. So the shocks created in the wind blown by massive stars. Especially, it is known that Wolf-Rayet winds are enriched in neon-22. So this could be a good indication that some other objects are playing a role in accelerated cosmic rays. Wolf-Rayet wind, but not only. We had other results. Another famous result comes from the detection in gamma rays of massive star clusters. Here you have an example. So this is luminosity as a function of energy for various objects, the Sirius cocoon, the central molecular zone, Westerlund 1. And they were able to detect a spectrum in gamma rays, but also to detect the spatial extension, so as a function of distance, the content in cosmic rays. And this profile here is a 1/r profile. And this is actually what is expected from a continuous injection of particles in the ISM from the source. And so this has been seen as a very strong indication that the stellar clusters, massive star clusters, are playing a role in producing cosmic rays. This measurement of the extension of gamma rays, and therefore the parent particle spectrum, as a function of distance from the source. In fact, the possibility of accelerated particles at stellar clusters, young, old, has been discussed for a long time. Just to give you a sense, if you look at the dates here, you see that this work has started from the 80s, and you have a lot of work still going on now, and I could add a few references. It is understood that if you have a young stellar cluster, it seems that you expect something very spherical, quite neat. And as this cluster is getting older, the supernova remnant starts to explode. So the shock and everything is becoming a little bit messy. And people have run simulation of this. And this is one example where you see clearly from a compact young star cluster the wind termination shock. This is from MHD simulation. Whereas if you have older clusters, you don't see the wind termination shock anymore. But so this environment, young, old star cluster is understood pretty well now and getting better and better. And also could explain how you get the spectrum that is steeper to p to the -4. So on the main sources of cosmic rays, what do we have? I discussed supernova remnants, wind termination shock, super bubbles, which is another possibility of bubbles inflated by the repetition explosion of supernova remnant. And we have all this problem, the energetics, the injected spectrum, getting to the PV range, getting enough PV protons, not only getting there, but getting enough PV protons with a hard enough spectrum. What about the bumpy bump, and so on? And if you try to see if those different candidates can solve these problems, the answer is yes, no, yes, maybe, probably, I don't know, maybe, unclear, maybe, yes. So the message here is what? Is that it's not easy to solve everything with one class of sources, which is not very satisfactory. I mean it's not very satisfying, philosophically speaking, because it would be clear and neat to have just one thing solving everything, and then you got your answer. It looks like you have a mixed contribution from various objects. An example of work where they've tried to understand this mixed contribution is this work by Tatishev and collaborators, where here on this plot, you see the abundance of cosmic rays for different types of cosmic rays. So not only protons. Protons are here, but you have all the different species measured. Especially in this work, they're trying to understand the overabundance of some cosmic rays that's called refractories. It's a class of cosmic rays that are likely to be found in dust. Over the volatile, the cosmic rays that are not found in dust. And they were testing for different models with a different composition. You see that you have winds in superbubbles, a mix of different phases of the interstellar medium. So the warm neutron, the warm interstellar medium, the cold neutral, and so on. So they were discussing different possibilities and trying to fit those data. And they found that the most likely scenario to account for the abundance of cosmic ray would be a scenario where most cosmic ray come from superenvironments in superbubbles and a minor 5% contribution from wind termination shock of young stellar clusters, so a mixed contribution. Finally, to give you some very recent result, a paper that came out a few weeks ago, I think, not so long, and results from observation of LASSO again, detecting the very high energy gamma rays from microquasar and identifying them, re-identifying them, because they've been discussed already in the past, as potential sources for the PV region. And you see that you have some paper coming explaining again, so this is again the local cosmic ray spectrum of protons. This is the PV range, and they show how with the usual sources, whether they are superenvironments, massive stars, you would provide this part of the spectrum. And if you add another component coming from microquasar up to the PV range, you could nicely explain the entire proton spectrum up to the knee. In fact, and I'm almost there, you also have some more fundamental issues that are arising. So this is not very consensual, but it's just an interesting possibility. People have been able to measure the helium and proton spectrum at low energy. And so this is only measured up to 10 to the 3 GeV. And if you do, so this is where the measurement ends. If you do a very wild extrapolation of this, it could be that at higher energy, reaching the knee, around the knee that we measured is not only due to protons, but also to a fair bit of helium. And this would, again, complicate all the conversation that we are having on the origin of PV particles. Because if the PV protons is not proton anymore, well, that's complicating the protons. So it opens many other questions on how you discuss not only the PV knee, but also the contribution right after from the various accelerator, and how do you explain the spectrum after the PV, the knee. So, as a quick summary on this little introduction on the origin of cosmic ray and gamma ray astronomy, you see that the very famous superenvironments paradigm for the origin of cosmic ray faces many problems. How do you accelerate the nice spectra to provide the local cosmic ray spectrum? What's the spectra not only accelerated but released in the interstellar medium? How do you reach the knee PV particles and beyond? And how do you account for the various deviation and features in the spectrum? That's not obvious. You have other candidates, such as star clusters, and asking that have to answer the same question, by the way. And it seems that mixed scenarios are often favored. Well, it's a pity because then you have more parameters, so it's hard to get a firm, definitive answer on all this. In the coming years, France is highly involved in this new observatory. It's called the Cherenkov Telescope Array Observatory, built in Chile and in the Canary Islands. We'll be able to probe the differential spectrums, the spectrum as a function of energy, in the 100 TeV range, which is exactly what you need to clearly understand what's happening in the PV range. Not only do you will have, I haven't shown the resolution, but well, so you have 100 TeV range, and you'll reach a finer angular resolution that what we have with current instruments such as HESS. So that will be very helpful to study the case of pevatrons. I had one last slide. Where has it gone? Sorry. I want to do a final advertisement. Final, it's up and down. What? Where is it? Nope. OK, I had one final slide where I was supposed to say, oh, yeah, that's the one. OK. I was supposed to say we have an ANR starting. It's actually starting in a couple of months. So the project is called Parmigiano. So it's very hard to remember. Particles transported from multiple accelerators, the gamma ray signal of extended source. It's a bit of a stretch, but it's a very nice project. This is involving people at Observatoire de Paris, at IRAP in Toulouse, and CPPM in Marseille. We will have 2 postdoctoral positions and 1 PhD position starting. So if you're ever interested, don't hesitate to reach out. And thank you very much for listening.
Thank you very much, Pierre. So you're on time. So we have time for questions.
different average?
The answer is yes. I mean, could be that the dependence on metallicity. But so far, the indication are, my understanding, are mostly from simulations. So from the measurements, if the question is how do you measure the cosmic ray spectrum from different galaxies, this I don't know how people do it. I don't know if it's possible. So the indication we have is mostly from simulation, which is, yeah.
But it may depend.
It may depend, yeah. Yes.
I didn't understand how you measure the atoms.
How did this plot here?
Yeah, how do you get from observation the type of atoms?
So yeah, so this is a compilation of a variety of experiments here. So actually, they provide reference, but those references are the reanalysis of a variety of experiments. So depending on the technique, as I showed in the very first slide, I showed you like 3 experiments, AMSO2, Dampe, and so on. So the different experiments we have in space, on the ground, sometimes they're able to differentiate, depending on the calorimeter they use, depending on the technique, they're capable of differentiating between the nuclei. So the answer is it completely depends on the technique that people are using and the detectors. But this is really a compilation of decades of experiments and variety of techniques.
And CTA is able to measure which?
So with CTA, you do have the gamma rays, okay, that can be mostly coming from protons, nuclei, electrons, and you can do a little bit of direct particles coming in the atmosphere and trying to understand what they are. But to be frank, I don't really know how much we can differentiate between. So we can differentiate between, is the cascade of particle, the cascade coming from a proton or gamma rays? We can differentiate, is it coming from something very heavy and not a protons, but like if it was iron or something? But differentiating between a carbon and a proton, I'm not sure that's the right instrument to do so. But I would have to ask to people expert on this. But so the answer, sorry, is a very poor answer, but it really depends on the technique. But yeah. With Cherenkov instruments, it's not obvious to do.
I was wondering the difference between LASSO and Hawk. Like, is Hawk able to detect the electron volt range?
Yeah, absolutely. So Hawk is mostly American, and LASSO is Chinese. And so that's the first difference. But no, the principle of this, LASSO is bigger. LASSO is installed in a different location and so on. But the principle at the core of it, like having photomultiplier in water tanks or so on in a fluid that will detect the Shaker light to reconstruct, it's basically the physical principle is the same. But as I said, LASSO is a bit bigger. They have 2 types of detector, not installed in the same location, not same altitude. They cover, the array is larger. So as you go higher in array, your resolution is changing. But the principle is the same. And also, they're both all sky survey, because since they're not observing like lights from, so they don't need, if you, the S and CTAO, those are atmospheric Cherenkov instrument. You need a perfect dark sky, no moonlight. Actually, you can have a little bit of moonlight, but it's more difficult. So you need a sky to observe. LASSO, Hawk, the same. You can observe every day, all night, every day. It's all good. It's a 24-hour duty cycle. But it's pretty similar. That's my. It's just a specificity of the instrument. LASSO was built after, a bit more money, a bit bigger, different size of different equipments. So, yeah.
So LASSO has been able to detect more in this range because of size, or because of our
Well, okay, because of size, because they have mixed detectors, because I'm trying to think of a good answer. But yeah, the sensitivity is better, not intrinsically because of the technique, because of all the steps that have been made better. For instance, there is so Hawk, there is this project to build SWGO, which is the Hawk South. This will be better, improved compared to Hawk as well, and this will be somewhat a competitor of LASSO in a sense. Not competitor, not seeing the same part, but on the same level of resolution. I think.
Thanks a lot for the talk.
Yeah.
You mentioned a lot compact objects of stellar masses. Can you tell us something about like AGMs? Do we expect a minor contribution overall from AGMs?
So that's a very good question. If you look at your TV sky, not doing this distinction like galactic, cyclic, most of the objects we see in the TV range are AGN. So we see AGN, especially flares of AGN in the TV range. So there is a clear, undoubt indication that you have particle acceleration, the highest energy in AGN. The problem with explaining this variability is an entire problem because we know the jets of AGN, inside there are probably shocks, there's a lot of turbulence, there's a lot of things happening. So not only when you're trying to make sense of AGN data, not only you want to explain acceleration at high energy, but you want to explain the variability. So clearly there are accelerated particles, and they are accelerating particles up to very high energy. Now their contribution for the local cosmic ray spectrum that we have in the galaxy is unclear, because this is injecting accelerating particles. So probably the contribution is to the extragalactic part or transition. But for the galactic part, and this is something I didn't want to get into too many details, but we know that the cosmic rays at low energy are confined somehow in the galaxy. So cannot come from extragalactic sources a priori. And so to answer your question, yes, definitely AGN well seen in the gamma ray sky, accelerating particles with a very rich phenomenology in physics, but probably contributing at higher energy if they're contributing. Yeah.
No more questions?
And you didn't talk about that, but do you also explore the dark matter annihilation process in the gamma?
So yes, there is an entire program to detect dark matter, or to attempt to put limits on dark matter candidates with CTAO, for instance. So this is what's called non-direct detection, right? So there is an entire program, and I don't know what more to say. I'm not involved in it personally, but it's a possibility, yeah. So they're trying to put limits on the cross section, and as they've done, by the way, with S also, but in CTAO, yeah, they work. A lot of people are working on this. Yes, that's.
Yeah, so probably I missed something. But did you say that there is the PPV phase of the supernova only lasts for a few hundred years?
I said that nobody knows. Nobody knows. But with our current understanding of what's happening in particle acceleration superenvironments, it will be highly unlikely. Okay, all the superenvironments we observe, the gamma rays seems to be cutting off. So there's a priori not a lot of PV particles there. Of course, now the problem also is that we go into detail, so you have an exponential suppression, and if you're able to probe like half a particles every century, and you say it's a pevatron, okay, you have half a particle, but that's not enough, right? So when I'm saying acceleration of PV particles, I mean enough PV particles to explain the cosmic ray spectrum. So in most supernova remnants, the gamma rays is indicating that you don't have enough PV particles. If you do a little bit of theory and so on, you realize that only a few, with our current understanding, only a few objects will be able to accelerate PV particles, and this would not last long. It will last typically a few centuries. So that's correct, yeah.
But then that cannot explain the numbers of SNR that we observe.
So the number of SNRs we observe in PV is 0 so far. So because all the supernova we observe are in gamma rays, but typically 10 TeV, not 100 TeV. So this can be explained. That's okay. Yeah, 43, but that's 43 seen with LASSO, but most of the sources, they are associated with a pulsar wind nebula, not with the superenvironments, which is the remarkable, because 10 years ago, in many places, people were writing like, when we find the supernova pevatrons, they were not even mentioning supernova. It was obvious, like if you have a pevatron, that's gonna be a supernova remnant. And now, like most of them are clearly not associated with supernova remnant shock. So that's a big shift in the, I think. Thanks.
Okay. So, yeah, thank Pierre again.
Thank you.